Now, after the atmospheric refraction, let us come back. So, first of all, before we thought that white is the color of light, and other colors are formed by passing white light through various things. Now, clearly, we know that that is not true. White light is actually a combination of all these colors. But what exactly does it mean by different colors? Like, what is the change between violet light and indigo light, violet light and red light? What exactly is changing because of which they are looking different? We have to know that, no? So what is happening is, I had told you in the beginning that light is actually a wave. We have wave nature of light and particle nature of light. Whenever we see reflection, refraction and everything, we feel like light is traveling in a straight line. Okay, but if the object that it is, see, if you place a big thing here, for example, see, these things are 400 nanometers. You know how small a nanometer is? Nanometer is 1 by 10 power 9 meter, means 0.0000 zeros and 1. Just imagine. So that is so small. So if we place such small objects, then obviously we will be able to notice the wave nature of light. But if we place bigger than that objects, we will feel as if the light is traveling in a straight line. So what is that which causes colors is different wavelength of light. Okay, so violet has a shorter wavelength. What is wavelength? See, this is a wave, like this. What is repeating again and again and again? So this thing is repeating. So this thing is repeating. Here also it was there, now again it will come, again, 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 again. So that whatever is a repeating item, the the length of that repeating item is called the wavelength. Okay, so here see, that is small. Now of red, the repeating item, that is the wavelength, is little bit less, little bit more, it is elongated. So violet has the least wavelength. Progressively red will have the highest wavelength. Okay, so now let us see what is scattering. This scattering is very important. This is actually why we notice most of the things that we notice in nature. Okay, what is scattering? When a beam of light interacts with a particle of matter, it is redirected in many different directions. This phenomenon is called scattering of light. So when there is a particle, light comes, and if it is a big particle, probably it will get reflected or whatever. But if it is a small particle, it will behave differently. It will get scattered in different directions. So one thing is, some light will get reflected, some light will get refracted, some light will get scattered. So scattering is redirection of this incident light in different directions. How? So what, there is a law for it. Different colors are scattered more than other colors. So one, maybe red is scattered very less, but violet is scattered more. I'll show you why that happens. So what is scattering? Scattering is basically uh, when the beam of light is redirected in multiple directions after hitting the particle, it is called as scattering. First of all, let us see what is the for like this is not, this formula is not there in the syllabus, but I'm just going to show you for your for understanding it, but it is not there in your textbook. But just so that you can understand better, I'm going to show this. First of all, what is the scattering of light dependent upon? In refraction, what was happening is, if the light is coming, the light will bend more towards the normal or away from the normal based on whether it's a rarer medium or denser medium. Okay, and it would bend more towards the normal if it was little more denser. It would bend a little bit lesser if it was less denser. So refraction of light was dependent on the medium. What is scattering dependent upon? So what scattering is dependent on the wavelength of light, that is the color of light, and the size of particle it is hitting. It depends on both the things. Okay, so how is it dependent on the wavelength? Wavelength is denoted by this symbol lambda. Okay, you don't have to learn it, just for the sake of this particular video remember it. So the wavelength is this lambda. Scattering is inversely proportional to lambda power 4, which means if if it's inversely proportional, it means lesser the wavelength, more is the scattering. So scattering will be least for red, highest for violet. Then scattering is directly proportional to d power 6, where d is the diameter of particle. So this is so it depends on two things. It depends on the wavelength. It is inversely proportional to wavelength. More the wavelength, less the scattering. But more the size of the particle, more is the scattering. Okay. Okay. So now we have to see the different cases. First case is when particles are of size lesser than wavelength of light. Okay, so wavelength of light is this much. If there are particles which are very much lesser than wavelength of light, okay, for example, atoms of or molecules of oxygen, nitrogen, carbon dioxide, all these are very, very small. They are very small compared to wavelength of light. Okay, so then what happens is, okay, what happens is in cases like that, we know that scattering is proportional to the diameter, that is the size of the particle power 6. But since the size of particle is so small, we can ignore this. We can consider its dependence only on the color of light. Okay, if you are facing confusion, then you can again write back to me and I will reply, okay, in the comments. See, because the distance is because the size is very small, we are going to ignore this and we will consider only the wavelength. It is inversely proportional to wavelength. So in this case, where the light is interacting with particles which are very much lesser size than its wavelength, then we only consider the the dependence on color. What is the dependence? Violet is scattered the most and red is scattered least. So this is why sky is actually blue. You might ask me the question, why is the sky blue and not violet? At least you know that it is not red, because when the sky is, what is more scattered, the colors towards violet color are more scattered than colors towards, so colors towards blue are more scattered than colors towards red. Red is least scattered. So because blue is scattered means it is sent out in all the directions. That's why sky is blue. White is not violet. That is advanced concept. Okay. Let me just tell you in one line. What happens is scattering is also there is a scattering function, but also our eyes are most sensitive to blue. So even though violet is scattered, but we see more of blue light because our eyes are more sensitive to blue light. You can forget about this, but you just know that blue is, the sky color is blue because the wavelength of blue is lesser, because of which it is scattered more. Let us look at one video for this.
Most people would say we can't see air, but what if we can? You can see air if there's enough of it. You see something when light bounces off of it or is transformed in passing through it. Air does affect light, but not much, so it seems invisible. But when you put a few miles of air together, it gives a lovely blue color. Okay, now you know that you can see air. But why is the sky blue? To answer this, let's start from the sun. The sun sends a beam of light which carries about every wavelength from X-rays to radio waves on its...
See, there are more things than colors. Okay, so white light, we have seen, what we have seen is, we thought white light is made up of different, all these colors. But white light is not just that, it has other invisible parts also that earth will filter. Okay,
its 8-minute trip to Earth. The Earth's atmosphere will trim this beam into a narrow range of wavelengths, and that light appears white, a mixture of all the wavelengths from violet to red. When this sunlight hits an apple, the apple absorbs light with all the wavelengths except red, and this red light is reflected back, which makes the apple look, red.
See, this is why we see colors. So first of all, when we see red, it means that particular thing is absorbing all the other colors but is reflecting red. Leaves are green because the leaves are absorbing all the other colors and reflecting only green.
Red. But why is the sky blue? All the atmosphere is made up of a lot of different gases like oxygen, carbon dioxide, etc., but it's also got dust and dirt. Now, a physicist named John Strutt figured out that light gets scattered as it travels through the atmosphere. And how much it scatters depends on 1 over the 4th power of wavelength. Red light has a longer wavelength, so it scatters less and just washes over the molecules present in the atmosphere. But blue light has a shorter wavelength, so it scatters more and interacts with the molecules present in the atmosphere. But wait a minute. Violet light has an even shorter wavelength than blue. So why isn't the sky violet? This is because the sun itself sends out less of violet and more of blue. Check out this solar radiation spectrum.
This is also true. So sun first of all sends more blue light than violet, and also our eyes are more sensitive to blue light. So there are two reasons. I think this graph and all will be too much for you.
These cones are
So you can watch this video, of course. I'm going to put the link in the description. But here I'm going to forward some parts. I think that's enough. Okay, so now we saw why is the sky blue. Okay, now let us see why is the cloud white. See, in the cloud, what are the particles in sky? The particles were oxygen, carbon dioxide, nitrogen. In the cloud, it is big water droplets. So the water droplets are much bigger. So this is 480 nanometer. That is, we cannot see only how much small that is. But water droplets we can see, it is very much big. It is definitely like much bigger than the wavelength of light. So what happened here? When the wavelength was bigger than the particle size, we ignored the particle size. But here with water droplets, the particle size is much bigger than the wavelength. So we can ignore the wavelength. That is, we can ignore the colors. So since the particle is particle size, that is the large water droplets, is obviously same. Just because red color goes, it doesn't mean the droplet will become small or anything. No. So it is same for all the colors. So the scattering of light for this is independent of the color. Even if red comes or green comes or blue comes, the scattering is almost the same because we are ignoring the lambda here. We are ignoring the wavelength because the particle size is so much bigger. That's why, because all the colors are reflected equally, we see the cloud as white. Why? All the colors mean combined is white. Okay, all the colors scattered equally, thus we see it is white. Now, why is the sun white during the day? So during the day, when we are seeing, let us assume, okay, see here, two rays we have taken, both of them are white light. After coming, it uh, from this ray, the blue light has gone here. We will not see blue light here. It has gone scattered away. Red light is coming. This is coming. Now from other rays, here we can see red light, blue light. So both blue light and red light are coming to our eye, and all similarly there will be many other rays. So we can, all the colors will come to our eye and we can see white. But at the morning and evening, what happens is the sun is not here, it is very far. Okay, so you can imagine earth has rotated, so when sun will not change its position, but we will feel like sun is here. Okay, because the earth's rotation. So let us, sun is far, then it has to travel a longer distance. So this ray that was there, two rays we had, no, this ray will not be there only. No, here only this long ray will be there. So if this long ray is there, it means we are getting red, but orange and some yellow and green, but other colors are getting scattered away. Okay, because of this we see only red color. And the sky also, Be- other colors will not be able to travel that much, because of which the sky also will become red. Let us look at the video for this again. So why is the sun and sky reddish orange during sunset and sunrise?
By reddish orange during sunset. Well, at sunset, the sun is a lot lower in the sky, and the sunlight has to travel through a lot more atmosphere to reach your eye, which means blue light has a lot more time to scatter all around. And what remains is the red light, which reaches our eye. Okay, but why are clouds white?
This we anyways saw. We can see
Cloud
again.
droplets are large enough to scatter all visible wavelengths more or less equally. This is called
Okay, this is we need not learn about it. Okay, so we now know what we now know so many things. We know why is the sky blue, because blue scatters more than red, so blue becomes much more spread everywhere, so blue we see. And why is the cloud white? Because here all the light is scattered equally, because the particle size is much big. And we know why is the sun white during the day, because all the colors will reach us, because the sun is not very much far. But in the evening, the sun will be much lower in the sky, because of which it has to travel a longer distance. So blue and all will get scattered away, only red will reach us. Now, so in this clouds, we had particle sizes much bigger than the wavelength of light. And in the atmosphere, that is in the air, we had particle sizes much smaller than the size of the wavelength. But in what happens if the size of the wavelength and the particle size is same? This the particles in a colloidal solution have a almost same size as the wavelength of light. Here what happens? Okay, the light beam becomes visible. See, you might have noticed this through the window and all. If the light is coming, you can see the beam. Usually you cannot see light, but if dust particles and all are present, then you can see the beam of light. So this is because the dust particles are very small. They are almost equal to the wavelength of light. So that's why the beam of light becomes visible. This effect is called as Tyndall effect. Let us look at one experiment. First he took first first we take water, okay, and then he put sodium thiosulfate, and then he put concentrated sulfuric acid, okay. Now he has left it for some time. Now see, can you see the beam of light here? See, the light is there, we can see the light coming out, but you cannot see the light here inside. We cannot see a beam. But now, because he is going to put this sodium thiosulfate, he is going to convert this water into a colloidal solution. Now you can see the beam. Slowly we are able to see the beam. See, now completely we are able to see the beam of light. What is happening? Why is it turning blue? Let me forward a little. So see here, now we can see this has become blue color, but we can see the beam, okay, because it is a colloidal solution. Particles now are actually, what is the particle, because of the chemical reaction, sulfur particles are here, and they are very small, uh, and they are almost equal to the wavelength of light. So because of that, the light beam becomes visible because of Tyndall effect. Also, what light are we seeing outside? Initially we were able to see white light only, But after we put these things, gradually we are seeing this red light. Here it has become blue, but here it has become red. Why? See, blue light scatters more than red light. Okay, because of which blue light has scattered up in all the directions here, but red light doesn't scatter that much. So red light will just not scatter, it'll come and it'll come outside without scattering. Blue light has scattered everywhere, so we can see blue here, but red light we can see. By this we can also see, kind of understand why is the sky blue, no? Because blue light is scattering more. Even though sky is not a colloidal solution, but still it has smoke and dust particles and so many things. So we can try to understand that blue light is scattering away, but red light is not scattering and it is reaching the end. That's all. So we have completed this chapter. Thank you. If you have any doubts, please don't feel hesitated.